So this is a schematic diagram for nuclear fission reactor. You can see. So here we have different parts. So I'm just showing you that the core region of the nuclear reactor, nuclear fission reactor. So this is just a schematic diagram of that core region where this fission reaction happens. So externally there will be different connections to these reactors, and all those things are very complicated, but that we are not going to discuss here. But we are just considering that the innermost part of that reactor where we have that nuclear fission happens. Okay, so that part is this core region of that nuclear reactor. So we have different parts for this particular regime. One, you can see that fuel, and which is in that fuel rods. So you can just show this as your fuel rods also. Fuel rods, and these are the fuel. Fuel is inside that fuel rods. Then we have this reflector. Just note it down. Okay. So this is just a schematic diagram of that inner part, the core regime of fission nuclear reactor. So we have a reflector here. Can I just show you that this is the fuel rod, fuel rods, these things. Okay. So this is fuel rods and this is reflector. Then we have control rod here. I will write it here if it is not visible. Control rods. Then this is moderator. Moderator. Then we have fuel. Then we have here coolant. Coolant. So I will just explain what will happen. What is the functions, different functions of these parts. Okay. So first part is that fuel. What will be that fuel? In nuclear reactors, we are using nuclear fission. So the fuel will be, anyway, it is uranium. Okay. Mostly we use uranium. Okay. There can be some other radioactive heavy nucleus, but we mostly we consider uranium. Okay, I will just insert one new slide here. Okay, so that will be uranium, that fuel. I'm sorry, I'm talking about that fuel. Fuel will be uranium. So when you take that uranium, you have to take it from the earth crust, and it will be having different materials. Okay, so that you have to remove all other materials, like you will be getting that uranium from rock, some rock, rock like you see that ores, ores of that uranium. So when you consider that rocks, then you have to remove all other impurities, all other materials that is in that rock, and you have to extract uranium alone from that rocks, and then that uranium that has to be extracted from that what is called as unpure sample, we can say simply, or it will be from that earth crust, some form of rocks it will come, and that you have to do some chemical bleaching or other kind of processes. Okay, and you have to remove all other materials from it, and you take only uranium. So even that uranium which will be having this uranium that will be that we'll get from, I already told that from earth crust, that will be unpure. It will not, it will be containing different materials, okay, different chemical compounds. So we have to extract only uranium from that, and that can be done by bleaching or any other chemical processes. Okay, you can do some evaporation techniques and all those things accordingly. So after that we will get uranium. And this uranium itself, this is not only that uranium 235, you will be that you will be having some uranium 235, and then you will be having uranium 238. Okay, and also you will be having some other types, other uraniums which are not in this range. Apart from this uranium 238, we can have uranium 235 or 233, all those things, so etc. So some other uraniums. Okay, so what we can, you should not write this in your exams. So there will be other uranium elements. Okay, which means that isobars, different mass number. Okay. So uranium 235, uranium 238, that will be, we will be using for this nuclear fission process mostly. So this uranium 235, how much it will be? So this will be having around 0.72 percentage. Remember that this will be only 0.72 percentage. Okay, I'll make it a little more thicker. And this one will be, this one will be the around 99.275, something like that. So total almost 100, but still there are some more compounds of uranium that is possible, some other types of uranium, other isobars. So this much of percentage 235, this much of percentage uranium 238. Okay, so this one, you know, this one is fissile nucleus, uranium 235. You just have to excite it and it will undergo for that fission reaction. These are fissile nucleus. It does not need any high energy neutrons, all those things. But these are non-fissile nucleus, because this will not be undergoing those nuclear fission reaction with that thermal neutrons. No, uranium 238 will not undergo fission reaction by using that thermal neutrons. It needs more energy to cross that barrier. So these are non-fissile nuclei. This is fissile nuclei, uranium 235, and we need more uranium 235. But when you consider that sample which is extracted from earth crust, that all chemical processes and all those things are happened. After that, you will get uranium compound, and in that uranium itself, it is having 99.275 percentage of uranium 238 and only 0.72 percentage of uranium 235 and some other uranium isomers. Okay, so we'll be using this too mainly. So uranium 235 nucleus, so we need that one more as compared to uranium 238, but in nature we have uranium 238 as majority, and it is around 99.275%. Compared with this is not even 1%. Okay, so this is very small. So in order to increase this amount, I'll just write it here, increasing this amount. What I mean that the uranium 235 quantity we have to increase. We do one thing, we have to enrich. Okay, we have to enriching sample. So what is this enriching means? Enriching means we have to do some chemical processes in such a way that, for example, diffusion, okay, where you can distinguish between this uranium-238 and uranium-235, and you remove some uranium-238. Okay, that can be possible. Okay, so since uranium-235 is concentration is very small in this sample, when you take that from the naturally occurring sources, okay, so the sample contains only 7.72 percentage of uranium-235, and majority 99.275 percentage is uranium-238. So we have to remove some uranium-238 from the sample in such a way that the uranium-235 concentration will be a little more higher, and that process is called as enriching. Okay, this process is called as enriching, and this enriching we do this enriching process by means of some chemical process, for example, diffusion. Okay, so if you consider diffusion, which depends on the mass, okay, so we can do different kinds of techniques here for enriching process. So one such process is that diffusion. So when you do this diffusion, this is performed by mass difference, that uranium-235 and uranium-238 is having some different masses, mass number is different. So they will be having different mass. So according to that, we have to differentiate this uranium-238 and uranium-235, and you take some portion of that uranium-238 out from the sample. Okay, or otherwise you can centrifuge these samples, and there also we can distinguish uranium-238 and uranium-235, another method to do this enriching process. So when you do that, okay, now it is 0.72 percentage of uranium-235 and 99.275 percentage of uranium-238. So this is uranium-235, this is uranium-238. Okay, so 0.72 percentage, 99.27. So if 20 percentage of uranium-238 removed, so this process is called as enriching. So if 20 percentage of uranium-238 is removed, okay, then what will happen here? The concentration, that percentage is same. Okay, I will say, I should say that this is, suppose this is some how it is 100. So this is this I can take around 0.7 sample size of 0.72. If this is I make this as almost 100, so this will be remaining that 0.72. But from here, if you decrease that to 20, then that will come around how much it will come? 79, right? 79.275%. Okay, which means in terms of percentage. So if I write that in quantitatively, I will just write here. So if you consider that 0.72 here as your 0.72 percentage, okay. So if you let's say 20 percentage, if you remove, then it will become 79.275, right, percentage. Now let's say that this, if I remove this 80 percentage, I will say I remove this by 80 percentage. That 80 percentage of the uranium-238 from the sample is removed. Then what will be the quantity here? Then we will be having 19, somewhere 19 point some 3. We should say 3. So because 80 percentage of this quantity, so it is not 100. So 80 percentage of this, that that is around this 19.3 value. Okay, almost to 19.3. You can calculate that. So So only 20% is there. 20% of this value. So you just check that it is almost. I'm just taking this 275 all the things as 3. So you just check how much it will come. It will be almost this value. This is not exact. You can calculate how much it is exact. So almost in this range it will come. Then if you calculate what is percentage now, then this will be having around 3.5% now, because 0.72 in 19.3. Okay, still it is only 3.5%, and remaining 96.5% will be that uranium-238. Still, if you remove 80% of that uranium-238 by diffusion or centrifugal method, if you remove uranium-238 from that sample, still it is only 3.5% of uranium-235 and 96.5% of uranium-238. If you consider that whole sample, right? So just check these calculations also. If it is wrong, you can tell me. So this is just 0.72, and you divide this 0.72. You take the percentage of this 0.72 to this, for example, 20. Okay, so let's say this is 0.72 plus 19.3, total you get 20 almost. So then you divide 0.72 by 20, that will be coming out of this value. Okay, you just check that, and then you have 19.3 divided by 20, that is coming around 96.5. So almost like this, which means that still after enriching process, after removing that uranium-238 from the sample, some percentage of that from the sample is removed, then still you will get only 3.5% of uranium-235. So this is your fuel. So this combination is your fuel, that 3.5% of uranium-235 and 96.5% of uranium-238, which are your fuel. This is the fuel of your nuclear fission reactor. So these are the uranium, which are the fuel for your nuclear reactor. Now this fuel, this is nothing but this uranium after enriching process. Okay, this uranium has to be converted. This has to be converted to what is that, pellets. First you have to make it powder. So first convert into oxide. Oxide powder, and then it has to be converted into that pellets form. I don't know whether you know this pellets. Okay, pellets that has to be made from this powder, oxide powder. Okay, then that pellets has to be stacked together. These pellets, I'll just then I'll just write then pellets are stacked together. Okay, so one after another, but one after another. And this will be in some zirconium alloy tube. To make 1 unit of it, that sample, and many such tubes forms cluster of it. I'm just writing that note. Okay, I will just check that unit to make so this is after another one after another in some zirconium alloy tube. Okay, I will just erase this. This is not recorded. So, just continue from here. Okay. So this is just my note, so it is not that important. You can refer in textbook also. So this is the stacked together one after another in some zirconium alloy tube, and many such tubes forms cluster of it. Okay, forms. I will say this is many such tubes. I will just bracket it is many such forms. Tube forms. I can just I write. I should not have written here. So I'll just many such. Just write here. So zirconium alloy tube and many such tubes which are called as clusters, which means many tubes are there together, that is called as cluster, forms one unit. So what I mean by this, you may not be familiar with these pellets. So if you have any kind of powdered form, okay, any powder, any kind of powder you imagine, any titanium dioxide powder or any chemical powder, okay, you press it in between some metal piece or something, okay, and then you will get some kind of shape for that powder with some solid like structure. But you might have experienced it with some powders, like if you have some metal piece here, okay, and another metal piece here, and you put your powder somewhere here, you apply some pressure with this whatever metal piece is this, apply pressure on this powder form, then it will convert into something like some shape like this, and it will look like some solid form. It will be very rigid. Okay, so this is called as a pellet. Simply, I'm just putting it simply. You had to make some sampling techniques, or some chemicals you have to add, all those things. But I'm just writing, giving you that simply make that powder into in between some metals, hard metals, and just apply some pressure on those metals. Okay, then it will form this. This is the powdered form here. Okay, this is the powder form. Then it will convert into some solid like structure. That is the pellet. Okay, so if you have pellets like this, you arrange that pellets in a tube like structure like this. You can check some videos for this nuclear reactor, that will be there, I think. So this is a tube. Let's consider like this. Some tube. So this pellet is arranged here Another pellet is next like this, one after another. Pellets are arranged one after another, and this tube will be made up of zirconium. So this zirconium tube, I am saying. So this is the zirconium tube, and your pellets are inside of that zirconium tube. Okay, these are your pellets inside those. So this is zirconium tubes. So if you have number of such tubes, then it is called as a cluster. If you have a number of such tubes, then it is called as cluster. Consider. I'm just I'll just draw here some more. So you have more number of tubes like this here and there. Then that will form cluster. That is number of tubes close to each other like this. That will form one cluster, which is having more number of such tubes. Then it forms one unit. Okay, and that is what you can observe in that schematic diagram also. I'll just go into that. So just to read this. So this sample, that uranium-235 and uranium-238, which has to be converted into some oxide powder, okay, from that oxide form into some oxide form in powdered form. So then it has to be converted into that pellet structure. Then pellets, they are arranged or stacked. Stacked means arranged in such a way that I just shown here. That stacked means one after another like that. Structure together, we can say stacked. So which means with some designed geometry that we are considering that pellets. So they are stacked together one after another. So you can just say it is arranged in such a way that one after another like that. So it is stacked together one after another, and then in some zirconium alloy tube, and that this many of such tubes will form this cluster, and that forms that one unit. Okay, so that's what we discussed. I just shown here in this figure. So that is your fuel road. You can see here these fuel rods. Inside that, we have to arrange these things. Whatever that we discussed here, that pellets, all those things will be inside that fuel rod. Okay. Then we have to go for something else, which is that another one, which is this moderator of this nuclear reactor. So I will just explain what are these moderators, why we use moderators. So if you consider that moderators, why we need that moderators? These moderators controls the energy of the neutrons. Okay. For example, if you consider that nuclear reaction, that fission process, uranium-235, that neutron plus this, that is given that X plus Y plus some new neutron. So whatever neutron you are given here, that is the initial neutron or that incoming neutrons that is absorbed by this uranium-235 okay. After that, these neutrons which are produced fission reaction, right? So these neutrons will be used for next reaction. Okay. So if this number of neutrons which is generated, which will be having more energy. So these are thermal neutrons, you know, These are thermal neutrons with a small energy, thermal neutrons. But these are coming after nuclear fission. This will be having energy in the order of mega electron volt, 1 mega electron volt, 2 mega electron volt in that range. So this will be having mega electron volt range of energy, but this is having only thermal energy, that initial neutrons. These are having thermal energy. And for the case of uranium 235, you need low energy neutrons to have this nuclear fission. So these neutrons, if you want to use these neutrons in the next fission reaction, next stage of fission reactions, then this neutron must be having low energy. So this mega electron volt has to be converted into low energy, thermal energy regime. Then only those neutrons can be used for fission reaction with this uranium 235. Okay, so the neutrons which are coming out after nuclear reaction, nuclear fission process, which will be having in mega electron volt of energy, that we cannot use for nuclear fission with uranium 235. So we have to reduce their energy from that mega electron volt to some few electron volt in that into that thermal energy range. For that we have to use these moderators to reduce the energy of neutrons. Okay, so for that we have to use these moderators, and when these moderators, normally we use water. So in that water we have H2O and that proton. Okay, proton we need from that water. So these neutrons will go, this mega electron volt neutron with that mega electron volt. This is having high energy neutrons, I am saying. So this is high energy. So this is high energy neutrons. High energy neutrons go, and these neutrons will hit with these protons inside that water, and that proton, when it hits these protons, and when these are high energy neutrons, and it will hit on these protons, and some of the energy will be transferred into that protons, and the when that neutrons are again coming out, it is energy will be lowered. It will get reduced. Their energy will get reduced. So these mega electron volt energy neutrons comes out from that rod, and it will be entering to that water which is surrounded by that rod. You can see from this figure. Okay, this gray color, which is that the this gray color, you can see these are the water or moderator, what you say. So when that from that rod, fuel rod, after nuclear fission, so I'll just show here, just I will explain. I will show one video if it is possible in the next class to explain all these things. So you have that road here, fuel road. Okay, so in this fuel road there will be uranium 235. Okay, initial fission happens inside this neutron hitting on those uranium 235, and that neutron which is coming out after that fission reaction immediately coming out from this fuel rod with high energy. So these neutrons are very high, having some very high energy. Here we have water outside that road, fuel road, and in water you have that proton. Okay, and that proton, when this neutron comes and hit on this proton, and it is scattered in some other different direction, that neutron. Okay, so this is having low energy now. Energy will be reduced for this neutron. Again, this will again hit another proton. Okay, again it will be scattered in some different direction, and the neutron energy will further again reduced, and the number of collision will happen in that that moderator. Okay, and that will reduce the energy of that neutrons, and it will reduce into that thermal energy. Then after that only that will come back into this rod and continue that nuclear fission process. Okay, So the second stage of nuclear fission is happening by using, will be used by this particular neutrons, which is formed in the first nuclear reactions, nuclear fission reactions. Okay, so that neutrons will be having very high energy, and that energy has to be converted, or which has to be lowered into thermal energy range. That is performed, or it is uh, doing by using these moderators. Okay, so it is achieved by using these moderators. Okay, so you just make some notes of this. I'm not giving that. Okay, so there is no time for that. So these moderators, which I have shown here, gray color. Okay, just outside this fuel rod. So first reaction happened, first fission reaction happens. The immediately that neutrons which are coming out along with that nuclear fission process coming out to this moderator, and it will interact with this moderator and reduces its energy, and becomes thermal neutrons energy, which will become thermal energy, and then come back again. It will go to that road. It will be having uranium-238 as well as uranium-235. But for uranium-238, fission process will not happen when the energy of these neutrons within the thermal energy regime. But uranium-235, for that fission will happen again, the second stage, third stage, fourth stage, etc. So multiple number of times fission will happen, and all those times that N will be used in whatever that fission happens that produce more number of neutrons. That neutrons will be used for the next fission reaction, and then this cycle continues. So for that, in order to reduce that energy of that neutrons which is coming out from that fission process, which is in the mega electron volt, to reduce that into thermal energy, that we use these moderators. So multiple scattering, multiple reflection, collision, all those things will happen inside this moderator, and the energy of that neutrons will be lowered into thermal neutron, and then it will come to that rod again, fuel rod again, and then again fission happens. This process continues. Okay, so this is the function of that these moderators. Moderators control the energy of neutrons which is coming out from the fission reaction, and that will be used for the next stage, nuclear fission reaction. And the next one is that reflector. You can see here, reflector. This reflector is nothing but it is used for any, if any neutron which is coming out from this core region, which is from that moderator, then it will reflect back into that region, into this moderator or core region of that nuclear reactor. So that neutrons which is coming out from this core region, where you have that nuclear reaction happening, nuclear fission process is happening. From there, some neutrons may get out. That will be reflected back by using this reflector. So there will be some surface which is made up of some material which will be reflecting those neutrons. We will not allow those neutrons to come out of this box, this particular cavity. Okay, so this reflector is used in some cases. Neutrons can get out of this core region, that will be reflected back to the core region by using this reflector. So that is the function of reflector. And then we have the coolant. This coolant, okay, this coolant we can use water here. Okay, and this coolant will be going through here, but since this nuclear fission happened here, it will produce very large amount of energy with those neutrons and doctor nuclei, whatever it is producing. It will be producing, along with that, it will be producing very high energy, and that energy will be used by those daughter nuclei and neutrons, and that energy will be transferred into this coolant. Okay, this coolant, that is water, and that water will be evaporated because it will be very hot here. It will be very energy will be very large here, so it will be very hot inside this cavity. Okay, in the core region. So when you pump water here, it will be get evaporated, and that this vapor, very hot vapor, which will be again passing through this pipe. So here it will be water, and when it reaches here, it will be evaporated into the vapor form, and it will be going through here. It will be having very high energy, which is in the very hot. It will be very hot, very hot vapor, which will be having some kinetic energy. All those molecules will be having very high kinetic energy, and those vapor which is coming through this particular pipe, which will be going to some turbine or something, and that will produce that electricity. Okay, that is how we get electricity from these reactors. So this coolant will be passing through, and in this hot regime, very high energy regime, it will become vaporized, and that will be used going through this pipe, and it will be used for rotating those turbines, all those things, to do some mechanical works. Okay, then we can use this energy for any electrical or other purposes. So this is the basic operation of this nuclear reactor. We have one more thing, that is the control grid. Okay, I will just explain in next class also something about this. So control grid is used if there is some excess number of neutrons are there. Okay, if there is some excess number of neutrons, suppose we need one reactions to be happened in a second, two fission process to be happened in a second, such kind of reaction rate we will fix for reactors. If that reactions rate is larger, which means that more number of neutrons are produced in the nuclear fission process, and more all these number of neutrons will be again hitting again uranium 235 and producing again nuclear fission. So number of nuclear fission per second will be larger. Okay, so nuclear fission rate will be larger in some cases. So in those cases, if you need to control that nuclear fission rate, then you have to use this control rod. You immerse this rod into this that moderator completely. If you immerse it completely, then many number of neutrons will be get absorbed by this control rod. Okay, normally we use cadmium. Okay, cadmium rods here as control rod. So cadmium rods will be immersed completely into this moderator. Okay, so that this when that neutrons comes and hit on this moderators, they will be going through this moderator after every nuclear fission, that will be absorbed by this control rod, so that the number of neutrons for the next stage of nuclear fission will be reduced in such a way that we can control number of nuclear fission per second happening in these nuclear reactors. So these are the control rods which will control the number of neutrons for the next nuclear fission in such a way that you can control fission rate in the nuclear reactors. Okay, so normally we use cadmium control rods, cadmium material rods. Okay, so if you immerse completely, these rods are immersed completely in this moderators, then more number of neutrons will get absorbed. If it is immersed partially, as it's shown in this figure, the number of neutrons absorbed will be lesser. If it is completely lift off from this moderator, then no neutrons will be get absorbed. All those neutrons will be again going for that nuclear fission, and the nuclear fission rate will be increased. So we can control that nuclear fission rate by controlling that number of neutrons by using this control rod. Okay, so these are the important the parts of nuclear fission reactors. Okay, then now we will discuss some more about the same in the next class, and we'll continue from here. Next, we have to discuss some four-factor formula and some more about the fission reactors.